Hello everyone and welcome back to the channel. I am currently suffering a bit of a bloody nose, which I guess is what I get for huffing too much glue. I'm sure all of you guys can relate. I'm making this video instead of watching March Madness, the reason being that my bracket is busted harder than me whenever I hear anyone talk about either Apache Flink or Corinna Kopf. Nonetheless, let's go ahead and make this video. Today it's actually going to be an extension of last week's, again about Napa, but I think an interesting one nonetheless. Alrighty, so let's go ahead and get back into it. So I'm just going to say right off the bat, if you guys didn't watch last week's video, I still think this one could be interesting, but you're probably lacking a little bit of context. It's not too long. You can definitely go double speed because really the main thing to note is that Napa is Google's data warehouse, and the way it stores files is in a way such that they have a sort order, right? And whenever you have files with a given sort order, you're going to be prone to hotspots. Just inherently, certain keys are going to be very popular. And so what they want to do in this paper is basically become better at partitioning their queries, where what partitioning really means in Napa is not in the traditional sense that we might partition a database table, right, where you're writing certain keys to certain distinct pieces of the table. But in this case, what it really means is that they have a bunch of these Delta servers because their architecture is something like, all right, well, we've got some Delta servers, we've got some F1 servers, and basically the Delta servers are responsible for like the scans, the filters, and the local aggregations. So basically any initial loads of data from Colossus, which is Google's file store, the Delta server is going to be doing that, and then they're going to do any initial processing before there's one original shuffle phase. So basically the idea is, depending on a query, we're going to allocate a certain amount of Delta servers or a certain amount of threads on those servers in order to basically do scans from the file system. And once we actually know that number, how can we basically split up the actual Delta files themselves in a manner such that we can get the best possible parallelization? Now, obviously, the way that you want to split these up is that, considering each thread on a Delta server can do relatively similar amounts of performance, you want to make equal segments of the table. That's not trivial, however, when you don't exactly know the sizes of the tables because you've got A, multiple deltas, and B, you can have hotspots within key ranges, and that's going to be a problem. So I'm going to go over the Delta files themselves in a little bit, but high level, we've got a bunch of B-tree indexes. They're all on disk. Ideally, we'll have them cached, but we'll talk about that in a bit. And keep in mind, these Delta servers are arranged temporally, right? So I can have a Delta from the last day, and that might get merged via a log-structured merge tree into a Delta from last week, and maybe that'll get compacted into one from 3 months ago. So the point is, they're probably increasing in size the further back that you go. And we have to read them all. So why is existing database partitioning not good enough for Napa? Well, there are a few reasons. For starters, the majority of literature when it comes to database or data warehouse partitioning focuses on, basically getting good data locality, right? So if you do hash or range partitioning, the idea is you want to keep data that's read together in a similar place. And Napa does that, right? Because they're inherently doing range-based partitioning where you're keeping the values for the same keys or similar keys in a table next to one another within one of these Delta files. So that's good. And if you have to split up a Delta into multiple disparate files, again, we're still doing that by range. So that's nice in the sense that you can get relatively fast range queries. And then besides that, there becomes a question of, well, how do you size your partitions, right? Because ideally, depending on how big or small they are, you're going to have a lot of different qualities of your table. So for example, if we use fixed size partitions, which a lot of people do because it makes them easier to rebalance or move around or something like that, you can have some problems. So if the partitions, or basically the files that you're storing in your underlying file system, are too small, basically now all of a sudden we have a ton of metadata. And metadata is not exactly cheap to store because typically we want that stored in a way that we can access it very quickly, often in memory. And so storing a ton of metadata is going to get really expensive and hard to maintain. And also it means at query time we have to read through all of that metadata, which in and of itself can be a very expensive problem. Despite it seeming like it would be a pretty easy thing to do, many modern database systems were kind of bottlenecked by how much metadata they had to read, and that becomes a problem. If the file sizes themselves are too big, now all of a sudden we have insufficient parallelism. The reason being that we have all of these preset partitions, we assign a worker thread per partition, and so if each one of those is, say, a gigabyte in size, and maybe the query that you're doing is 10 gigabytes, well, that's good because now you can get 10 workers, but what if you had 100 allocated to the query? Now 90 of them are not being used. Another note just on small files in general is small files work really nicely for balancing the load around, but a lot of these tables are literally petabytes in size. So if you're using like 10 megabyte partitions and you have multiple petabytes of a table, that's going to be many, many orders of magnitudes of partitions that you have to read from, and the overhead of doing so is simply going to make the entire thing infeasible. Another strategy that some people will do is this concept of like bucketing or using logical partitions within a file, where you just have one big file but then organize it into multiple partitions. And to some extent, that's actually kind of what we do in Napa, or that's eventually what they come to do via their B-tree architecture, right? Like, since you're organizing everything by key range, you effectively have partitions within a single file. That being said, that's still a bunch of metadata that you have to go through, and so Napa is going to try and do that in a more efficient manner. Another thing that they bring up in the paper is this concept of database cracking. So this is basically where certain databases will look at existing query patterns and kind of reorganize their partitioning scheme over time in order to deal with that. Now that's good, but again, that's still focused on the actual data organization of the table and kind of this right-time partitioning. But one thing that Napa notes that's kind of unique to their situation is that for every single query, they basically have a bunch of different, kind of SLAs or requirements that they need to satisfy. Now I realize there's a typo on my slide. The point is we're optimizing data layout based on query patterns to optimize the data layout. So just get rid of this 2 right here. Don't worry about that. But yeah, like I said, in Napa, one query that has a particularly high budget may require, having 100 workers that read for it because maybe it has to return in a second, and another query that can return in 10 minutes may just have 1 worker assigned to it. So basically the idea is we want to be doing more work such that we can do partitioning at a per query basis, and we'll discuss that in a little bit. And of course, finally, regardless of whether we're doing hash-based partitioning or range-based partitioning, certain keys in the sort order are always going to be hot. And so if you have an index on a couple of keys, within that key you may have 10 times the number of rows that you might on the one next to it. And so just partitioning by key range naively is not going to get this thing done. Just a quick reminder before we go any further, what do deltas actually look like in Napa? Deltas are basically immutable files, either in like a row-column hybrid oriented layout or in a pure columnar layout. But the gist is, if this is my delta for last week, you can imagine it's going to be quite a bit bigger than the one from yesterday. And then we also have a B-tree associated with it. So we're going to go into B-trees in a little bit longer, and we've covered them plenty on this channel. But the idea is, basically we have an index saying where certain keys lie on disk, and then we organize that in a tree hierarchy so that if, for example, I wanted to figure out where a particular key lived on a table, it would be logarithmic time for me to get there as opposed to having to do a full linear scan. That is by virtue of sorting the keys, of course. Cool. And then we also have this concept of differently sized deltas, right? So you can see this one only has keys between C and W as opposed from fully from A to Z. And it's nice that we have this because what it means is, if I'm doing a query where I say I only care about keys where the value is equal to Z, I can basically, queries for key Z, skip yesterday's delta, I can cut this guy out and ignore it. So it's good because I can do a lot of data pruning. Again, like I mentioned, these guys are ordered in a log-structured merge tree, so eventually what would happen is after a while, I'd want to compact these 2 files. Since they're both sorted lists, we can compact them fairly easily as opposed to having to do a global sort over everything. Okay, so let's get into the partitioning philosophy a little bit here before we really get into the algorithm, because that is when things are going to get a little tough. So basically, we want this to be specific to every single query. Again, this is good because queries have different properties to them, and we may need to make a bunch of different size partitions depending on what we're doing. Partitions should, of course, be well balanced. We don't want hotspots. Every worker should be handling similar amounts of load. Number 3 is that partitions should be determined progressively. So this is actually kind of the unique thing of this paper, which is that rather than reading all the data, figuring out the exact key counts in every row, getting perfectly balanced partitions, and then returning those for the workers to compute, that can actually take a really long time because you're effectively reading the entirety of the table first. Instead, what we want to be able to do is have these tunable error bounds, right? So for queries that need to return very, very quickly, we can basically tune the error bounds such that our partitions don't have to be perfectly balanced, and as a result, this partitioning calculation is very fast. For queries that can run longer, but we want to be more efficient, like a big batch job, we can take a while to do the partitioning calculation, and then we can have very, very exact, almost even partitions, which makes our query more efficient in terms of resources used per worker. So this kind of progressive partitioning allows us to handle both low latency and longer running batch jobs at the same time. Okay, and then finally, just to elaborate on that a little bit longer, basically this all kind of comes down to utilizing the existing B tree index that exists per delta file. So imagine this is one B tree for one specific delta right here. So we've got keys A through Z. Basically, let's imagine that when I have a number like this, 23 right here, what that basically means is, okay, for keys starting with A and ending before G, so not inclusive, there's 23 of those rows. And the way we get these is just by aggregating the counts of the rows at the B tree nodes that are below us. So for example, there are 4 keys that start with A and end before B. There are 0 keys starting with B, 12 keys starting with C, and so on. And so basically we're taking our normal B tree, where a normal B tree basically has all of your keys on one page of disk and then has pointers to other pages of disk so that you can logarithmically traverse down the tree and find the key range that you care about and where it lives in the actual delta file. And we augment it with these statistics right here about row counts. Now the reason that's so useful to us is because basically when we eventually want to determine our partitions, or the key ranges that make up each partition so that each partition is about equal, we can do so. So in this case, imagine we wanted to have a few different partitions. What we could be like is, oh shoot, there's 80 keys in this range over here. That's going to be the majority of the table. So maybe we throw down a partition over here, so maybe we've got like 50 keys over here and 50 keys over here or something like that, and now we have an even split. And so keep in mind that this is really good because if looking at the first B tree we're able to have enough granular information to get even splits, we've done this thing really efficiently. If, however, we're traversing the root level of the B tree and we see, okay, you know what, we don't have enough information here to get even enough partitions, then we can traverse down into the subsequent levels of it, but we do so lazily to ensure that we're not doing more work than we need to do. So that's kind of the whole progressive aspect of it. So let's walk through this a little bit more. This slide is going to get a little bit crazy. I'm sorry in advance for doing this to you guys, but I'm just going to walk you through it one step at a time. So this image right here is directly from the paper. I'm just going to reuse it because there's a lot going on. So basically what the image is displaying is if we were to find 2 partitions, so we're taking, we have 2 deltas right over here, right off the bat. We have 2 deltas, which are not necessarily the same size. In this case, they happen to be. And we want to split them evenly, such that one key range of both deltas is going to one partition and another key range of both deltas is going to the other partition, and they are relatively evenly balanced, right? And so the query that we're doing cares about all of the keys in K1 through K8. Even though it only shows delta 1 and delta 2 as having keys K1 through K8, if there were to be something like a K9 through K11 right here, we just wouldn't include that in our calculation that we're about to do. We would completely omit that node from what's known as our working set of B tree nodes. Okay, so basically what we do is we start out with these guys right here. So these guys are considered our current working set because they are the ranges of the root levels of both deltas B trees that overlap with the query, right? So assuming this is the top level of both deltas, basically we see, okay, K1 through K3 overlaps, K4 through K8 overlaps, K2 through K5 overlaps, K6 through K7 overlaps. So now we have to choose some arbitrary split point to determine how effective our partitions are. And in this example, they choose it such that it's basically all keys up to K4 are in one split, and all keys starting with K5 and beyond are in another split. So the calculation looks something like this. Basically, we know, okay, if this is our split, 15 rows for sure are on the left side of it. Now, what about for this guy right here? Well, there are 20 rows between K2 and K5 from delta 2. However, we don't actually know what the exact distribution of them is, right? We would have to traverse further into the B tree to figure that out. So all 20 of them could be on this side, all 20 of them could be on this side. In reality, it's probably some mix of the two. And the same goes with this guy right here, right? We know there's 20 rows between K4 and K8 in delta 1, but we don't actually know where they lie specifically. So we have a bit of uncertainty. So basically, if we're looking at partitions 1 and partitions 2, we know that the minimum number of rows in partition number 1 is 15, and the maximum number of rows is 75. The reason being all 20 could be over here, and all 20 could be over here in K4 from delta 1. That being said, if we look at partition 2, the same exact thing applies, right? So at minimum, we know there's 15 rows because there's 15 rows over here. And then we also know that it's possible all 20 rows could be on this side of the barrier on both of those B tree nodes over there. So basically, now we're able to calculate two things. We can calculate, number one, a size estimation for each partition, where the size estimation is just the average of the min and the max. And we can also calculate a margin, where the margin is the max minus the min. So in this case, the average is going to be 35, and this is the case for both partitions, and the max minus the min is going to be, let's see, 40. So ultimately what we do is we take 40 divided by 35 and compare it with some number theta, where theta is just a parameter. So theta is going to be our error margin. And so if all partitions have basically their size estimation divided by their size margin being less than theta, it basically means that we can stop our algorithm and we have good enough partitions. Otherwise, what we have to do is actually drill further into the B tree. So in this case, I'm going to run some things off here. In this case, what we'll say is, okay, maybe theta was not satisfied here. This isn't a good enough partition. We have too much uncertainty within our sizes, and they're not balanced enough because, you know, the size can fluctuate so much depending on where the actual keys lie in this guy and this guy. So what we'll actually do is we'll do another step of our algorithm called drill down. Where drill down, first it's going to find all of the B tree nodes that were cut by the given partition boundary. So in this case, it's this guy here and this guy here, because they're contributing to the uncertainty. The partition boundary splits them, so you don't actually know where the keys lie in this partition. Now let's imagine, for example, that, you know, we do our drill down, and then all of a sudden it turns out, hey, this guy over here becomes this, right? So actually there's 15 keys in K4, there's 5 keys that start with K5, and then everything else has 0. Now we have more information, and we can actually create a more accurate partition split. Cool, so hopefully that all makes sense. Basically, I'm now going to, you know, really formalize the algorithm. It's going to get a little bit confusing because there's a lot of text on this next page, but hopefully it makes sense overall. Okay, so here is going to be our overview. Like I said, across D delta files, as we saw in the last time, we want P different equally sized partitions, and we have some error bound of theta. We know how theta is calculated. We basically take the size margin, we divide it by the estimated size of each partition that we've computed, and we check if it's less than theta to be valid, otherwise it's invalid. So we start out with this concept called a working set, where a working set is basically the nodes across all B trees that overlap with the current query at the current level that we're at in the B tree. So when we start out on this query over here, the working set is basically all 4 of these guys. Great. Now, the first thing that we do is we create a list of something called candidates. So to find our candidates, we sort all of the start and end keys of the working set nodes. So in this case, our candidates are going to be K1, K2, K3, K4, K5, K6, K7, and K8, because those are the start and end points of all of these nodes. Great. The next thing that we do is figure out the total number of rows in the table that we've seen at the moment. And the way that we do that is just by summing up all of the possible, basically all of the elements in the working set. So basically that's 15 plus 20 plus 20 plus 15, which adds up to 70 total rows in the query. Now, because we have a number of total rows and a number of total partitions, this basically gives us an estimate of how many rows we want per partition. So we do that, but we create a cumulative sum of it, right? So in this case, there's only 2 partitions. So basically, you want a cumulative sum of whatever our split point is. We want 35 rows there. Let's say there were 10 partitions. What we would want is 10, then 20, then 30, then 40, onwards, all the way to 70. So keep in mind, like I said, it's a cumulative sum. The reason we have this cumulative sum is because now what we're about to do is pick a bunch of split points, where split points are just arbitrary keys that split up all of our candidates. So in this case, our split point is some sort of arbitrary key that's right between K4 and K5. Now the question is, how do we actually compute these split points? We're going to have to pick things. We're not going to pick them completely randomly. Well, for this iteration of the algorithm, the way that we pick a split point is by doing the following. We basically, at each potential split point, compute the minimum number of rows from the table start to it and the maximum number of rows from the table start to it. So in the case of this split point right here, we know that the minimum number of rows from the left side of the table to it is going to be 15. The maximum number of rows is going to be 15 plus 40, which is 55, right? We calculate that right over here. So we're going to say, okay, here's one potential split point right there. And we actually do that for every single key, right? So if I'm looking at all potential split points after every single key in the candidate list, for K1, for example, the cumulative sum and the cumulative minimum sum to it is 0, right? Because right here, if I were to put something right here, there's no guarantee that there's any rows that start with K1. That being said, the maximum possible rows, if I were to put my split point right here, is 15, because it's possible that all 15 of these rows are in key K1. So you actually do that for K1, K2, K3, K4, K5, all the way to K8. And then you evaluate all of those cumulative sums and basically compare them to your target cumulative sum, where our target in this case, if you recall, is going to be 35 because it's 70 divided by 2. Now, basically, we'll take the split points out of all of those candidates that gets us closest to 35, both for the min possible cumulative sum and the max possible cumulative sum. And that is going to give us some potential partitions, right? So now, in this case, right, I'm going to erase some more stuff. Again, we have these two partitions right here as delineated by this split point. And this is where we actually run that calculation from before, where for every single created partition, we find the size margin like we did before, we find the estimated size, and we compare it to theta. So let's say theta in this case is 1. If we do 40 divided by 35 like we did before, we know that's greater than 1, meaning that both of these partitions are invalid because this split point is a bad split point. And it's at that point that we actually go ahead and find the segments of the B trees that are cut by it, and we do something called the drill down, where basically, let's imagine, now we have these individual guys right here. Instead of looking at this entire node in aggregate, we'll drill down and use the mini pieces of that B tree that overlap with the query, and we'll replace that in the working set. So in the next iteration of this algorithm, we'll have this guy to consider, this guy to consider, this guy, this guy, this guy, this guy, this guy, this guy, and this guy. And then we're going to run our algorithm again. And we're basically going to do that until we terminate. Hopefully that makes sense. It's not overly complicated. Honestly, in the paper, it took me a while to get it, but again, really not too complicated. Cool. So before I end this video, we're going to go through just a couple of optimizations that they actually applied to the algorithm. Because I kind of gave it to you in like a mathematical sense of what the code looks like, but what do they do to actually speed things up a little bit beyond just a high level? So for number one, they do a lot of parallel I/O, right? If there's any time where you can make multiple B tree reads in parallel, you're going to do so. A lot of times, for example, we're doing drill downs on multiple different deltas at once, and you want to be doing those in parallel as opposed to sequentially. Number two is, keep in mind that we have these split point candidates right here, right? We've got something like this guy. Let's imagine that K4 is, a multi-column key, right? So it has like name and date. For our split points, we actually just want to use a prefix key. So in this case, just a key based on the name. The reason why we want to do that is the smaller keys that we use as our split points, the more simple comparisons are when we do them with other keys to determine whether a particular row of our table is on one side of a partition or the other. And since we're doing these comparisons so much, this is actually fairly significant. Cool. Another thing that we do is only drilling down into the biggest B tree. Remember that deltas are very, very different sizes. If I go over here, this guy is much, much bigger than this guy over here. And so even if we have an imbalance and maybe there's a part of this B tree that could be drilled down into, it's going to be a lot more impactful to drill down into this B tree because we're going to get a lot more information, relatively speaking. And probably it's going to be more impactful to solving our imbalances and require fewer disk IOs. So you only drill down into the deltas that are at the highest level. If you have really small B trees, you may not drill down. Cool. moving on, finally, like I mentioned, whenever you have a bad partition point, right, so you put a split point down and the partitions on either side aren't looking good, you have to basically determine which pieces of each B tree and each delta this split point cuts or overlaps with, such that you're not sure exactly where all the rows are. In this case, you've got a couple of options to make this computation relatively fast. Number one is that when you're actually creating the sorted list of things by just going K1, K2, K3, K4, blah, 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 what you could do is basically pre-cache with those all of the particular B tree nodes that they would be cut by for all potential split points. That being said, pre-caching those takes a lot of memory because you have to, it's going to be basically quadratic. So instead, what you prefer to do instead here is basically all you want to do is keep a sorted list of all of the currently considered B tree nodes on a per B tree basis, and then for a particular split point, you can actually binary search those sorted lists for every B tree, and then really quickly figure out which one of the B tree nodes that you're cutting with this split point. So for example, what that means is that for delta 1, that binary search would look like 1, 3, 4, and 8. And so if this split point is, for example, at 4.5, I can do a binary search really quickly and say, oh wait, you know what, I'm clearly cutting 4 to 8. And so you're trading off basically compute with memory footprint there, because that binary search is still relatively fast, but now you don't have to cache nearly as much stuff. Okay, let's go ahead and conclude this thing before my voice gives out. Basically, we've seen a lot of ways of partitioning tables at this point. We've seen hash partitioning, range partitioning, and just using fixed sizes or not using fixed sizes or making them adjustable or things like that. And to be clear, those still all come in play here. Like at the end of the day, Napa is doing range-based partitioning. They are keeping their files to certain sizes. They're not using gigantic files. That being said, there's still an additional layer of splitting up work that you need to do at read time because queries have different properties to them. And so being able to do this kind of progressive partitioning scheme allows you to basically fit all query profiles regardless of whether they need to finish really quickly or they can take a bit longer and get maximal performance out of them. So guys, I hope this was an interesting video. I haven't really heard of any other systems doing something like this, and it's a fairly new paper. So we'll see if it gets implemented more and more. I think one thing that makes this unique is the fact that all of these tables are sorted, whereas that's not the case, for example, in something like Snowflake or Iceberg typically. I mean, you could, but it really depends on what you want to do. So hope it was a useful one. I will see you guys in the next one, and have a great weekend.